organizers. So this is joint work with Petros and Elham. So we've seen this picture a lot during this conference, so I won't dwell too much on this setting because I assume everyone is pretty much familiar with this, except to say that we're taking a more cryptographic view of non-local correlations, in the sense that we have Alice and Bob, and they have these black boxes, and we don't know exactly what these black boxes are doing, but we're just looking at the correlations of their outcomes, and whenever their correlations satisfy either of those two properties, we say that they are non-local. So it should also be familiar that we have this result called Tsirerson's theorem, that if in quantum mechanics the maximal value that we can achieve for these non-local correlation is 2 root 2, and for example we can achieve it by having them share these phi plus Bell states, and having Alice, for example, measure the poly x and z observables, and Bob measuring x plus z and x minus z. So maybe now something that is unfamiliar is that the converse of Tsirerson's theorem is also true, and this is known as rigidity of non-local correlations, and it was shown in 2012 by Reichardt, Unger and Vazirani. So what does this mean? It means that if we observe, assuming quantum mechanics is the correct description of nature, if we observe close to maximal non-local correlations, then there exists some isometry phi such that the shared state of Alice and Bob under this isometry is close to a tensor product of Bell states and maybe tensor some additional junk state, and their local observables are close to the ideal observables that they will be measuring in the ideal strategy. So essentially what this is telling us is that if we saturate non-local correlations, we can uniquely, up to this isometry, determine the state and the strategy used by the two parties. So the proof of this is really nice, and I encourage you to read it because it's only 100 pages long. Okay, so we've also seen yesterday a talk about steering. So the setting is very similar to that of the non-local setting, except that now we actually know what Alice is doing. So she no longer has a black box. We know exactly what measurement operator she's implementing, and we have some characterization of the dimensionality of her Hilbert space. And again, if either of these two equations are satisfied for their correlations, we say that we have steering correlations. And analogously to Tsirerson's theorem, we see that for this particular inequality, the maximum value is 2, and it can be achieved. So it's also achievable in quantum mechanics, but it's also the mathematical maximum for that expression. And again, there is a strategy in which they share Bell states, and they measure these x and z observables. So if they do this, they will obtain the maximal steering correlation. So the title of this talk kind of gives it away. What we did is we proved the converse of this in the same spirit as the converse to Tsirerson's theorem. So before telling you how we did this, I just want to clarify the assumptions that we're making. So the first assumption is that quantum mechanics is the correct description of nature. So I'm sorry to disappoint people with supraquantum correlations. The second assumption is that, as I said, Alice is trusted, and we know that she's measuring these anti-commuting observables A0 and A1, and you can just take them to be the x and z observables, for example. Bob, on the other hand, is untrusted, so he measures some observables B0 prime and B1 prime, and the prime just indicates that they're untrusted. So whenever you see prime on some observable, it means it's untrusted. I don't know what it is. And we assume that these observables are two outcome observables, so they give outcomes +1 and -1, and they're also unitary. And the shared state is assumed to be prepared by Bob, so it's an untrusted state, and we want to show that it's actually close to a tensor product of Bell states. Lastly, we temporarily make this IID assumption that in fact the shared state is just a tensor product of the same state psi repeated over and over. And initially we'll have this assumption, and then we'll remove it and we'll get the more general result. So if we have this IID assumption, the setting that we have is called self-testing, in which we want to show that by looking at the correlations of their outcomes and assuming these correlations satisfy this close to maximal steering inequality violation, and knowing exactly what Alice is doing on her side, we want to show that the state psi is close to a Bell state, and also that Bob is measuring close to ideal observables under some isometry. And we can in fact show this, but for lack of time I won't give the proof of this. just to say that it involves some mathematics. And the interesting thing about this is that we can actually show that you get this bound that the state is root epsilon close to a perfect Bell state, and also the action of Bob's operators on this state under the isometry is close to the ideal action of his ideal observables x and z on the ideal Bell state. The bound is root epsilon close, and we can show that you can do no better than root epsilon close. So if you observe this epsilon close saturation of steering correlations, you can't get a state, you can't prove that the state is any closer than root epsilon except by some constant factor. So this is an asymptotic bound. Okay, now in the non-IID scenario, we have some general state between Alice and Bob, and we can no longer speak of having individual psi states in each run, but we can still speak about the reduced state in each run. So the reduced subsystem of what is actually measured in each round of measurement. And again, if we observe these close to maximal steering correlations using martingales and concentration inequalities for martingales, we can again show something similar to the previous result, but not exactly the same. So what we're showing here is that if you randomly pick one of these subsystems, if you randomly pick one of these reduced states, then that state will be close to the ideal Bell state, and the action on that state is close to the ideal action. And the bound this time is something like epsilon to the 1/6th, and we have no idea if this is a tight bound, and we'd like to somehow figure out if it is or if it isn't tight, but we have no idea. So essentially the statement here is that a typical state is close to the ideal state, so one randomly chosen state. So now we want, having proven this thing, we want to arrive at the tensor product structure, so to say that we have a tensor product of Bell states being that the state is close to this tensor product structure. So we might think, okay, I do k rounds of measurement, I use the previous result to claim that the typical state is close to a Bell state, and then I just repeat this n times to get n typical states, and I say, okay, all of them are close to a Bell state. But actually this is not, so in the end this will be what we do, but it's not implicit that this is actually true, because in principle there could be some overlap or adaptiveness on Bob's side, meaning that Bob could somehow reuse his quantum states that he already measured or whatever. And so if I pick a typical state in one round and a typical state in another round, it could be that his qubits are actually the same qubit. And we could invoke some reasons of monogamy of entanglement for why this shouldn't happen, but we do need some explicit proof of this. So the way we proved it is not using monogamy, but using this technique of Reichardt, Unger and Vazirani, in which we start by defining the so-called real strategy of the setting. So the real strategy is just the shared state of Alice and Bob and whatever actual operations they're performing on this thing. Then we have the ideal strategy, which is the tensor product of Bell states and the ideal operators acting on these Bell states. We also define this thing called the guessing strategy, in which Alice is doing the same things as before, but she's also guessing Bob's outcomes. So for Bob, the action on his side will actually be identity. He won't be doing anything. And Alice will be guessing his measurement outcomes based on her own measurement outcomes. And in this guessing strategy, we assume that the shared state is the one in the real strategy. And we also take another guessing strategy having the ideal state between them, but the exact same principle. So we also say that a strategy is epsilon structured if it produces close to maximal steering correlations. And we also say that two strategies are close to each other if their states are close to each other and their strategies are close to each other. So our objective is to show that in that case that the real strategy is close to the ideal strategy. So if we think about where these strategies lie in some sort of space of strategies, we somehow need to show that the distance between them is not that great, so that they're actually close to each other. So the way we do this is to consider this guessing strategy and to show that the guessing strategy is actually very close to the real strategy. The reason for this is because both of these strategies are epsilon structured. They produce close to maximal steering correlations, and they start off with the same initial state, so it can be shown that in fact they are very close to each other. Then the second guessing strategy is close to the first one, because in this guessing strategy, having Alice on both sides, we've eliminated the problem of adaptiveness. So there's no longer a problem that Bob could adapt his outcomes because Alice is guessing for him and she certainly won't adapt her guesses based on previous things. So then these two strategies will be close to each other. And then, trivially, the guessing strategy with the ideal state is close to the actual ideal state. So in the end, the real strategy will be close to the ideal strategy. Okay, so what can we use this for? I mean, the result is interesting in its own respect, but we can also use it for a particular application. And the most natural application that we can come up with is quantum verification. Why? Because in steering we have this asymmetry in trust. We trust Alice, but we don't trust Bob. And in verification, we have a trusted verifier who is computationally limited, cannot perform universal quantum computations, and an untrusted server that is able to perform these computations. And somehow the client wants to delegate the computation to the server and verify its correctness. So if we associate the verifier with Alice from before and the server with Bob, then we're in a very natural setting to use this steering result. So the way we use it is we divide this verification into two steps. In the first step, so we give Alice a measurement device, which is trusted. She shares entanglement with the server, and the entanglement was prepared by the server. So in the first part, we will use the rigidity result to show that these states are actually close to ideal Bell states, and they're being measured correctly by Bob. And once we have this determination, we can then use this to verify any arbitrary unitary being performed by Bob on his system, and in this way characterize any quantum computation. And the nice thing about this is that the measurement device can also be made untrusted, in which case we would use non-local correlations. But with the steering result, we get a vastly reduced overhead. So in the non-local setting, the current best protocol has like n to the 2000 round complexity. The steering one has n to the 13. So it's still far from practical, but it's definitely much better, and we think that we can even improve it to make it closer to practical. Okay, so to conclude, we've seen essentially that there is this correspondence between saturating certain types of correlations, like non-local or steering, and the ideal strategies associated with obtaining this saturation. And the way we prove the left to right direction, so that from saturation you can characterize the strategy, is by starting with IID self-testing, then removing the IID assumption, and then performing this trick with the strategies to arrive at rigidity and the tensor product structure. We also showed that there is a lower bound in closeness of order root epsilon in terms of the IID self-testing, but we don't know if the other bounds are also tight, but we like to think that they're not and that we can get better bounds. And we also saw that the most natural application of this is to quantum verification. So with that, I leave you with some references, and thank you.
Talk for a few questions.
I have a question.
Yes.
Yeah.
So what was your result exactly for the approximate case? Like, I guess in the Bell violation there's also this, of course I might not observe maximum violation, but just a little bit of violation. So I guess in the steering inequality case I might also...
So you're saying approximate, like if it's epsilon close to the maximal violation?
No, I don't mean epsilon close, I actually mean in the interval between 2 and 2 squared. So my epsilon is quite large.
Also, if epsilon, I'm not exactly sure. Like it's well, we made no assumption about epsilon except that it's between 0 and 1, and then we expressed everything as a function of this epsilon in the end. So I guess that if you have a very high epsilon, then your strategies and states will be very bad and very far from ideal.
I mean, clearly yes. I was just because I think the paper by Ben Reichardt and so on only works very well if I'm very close to the maximum violation.
Also, so you mean, yeah, it works very well because of the scaling as a function of epsilon. Like, so for example, in our case, because we get epsilon to the 1/6, then epsilon should be really, really small for you to have like very close to maximally entangled states. So what we did show is that we did like a numerical analysis in the IID case, because in the non-IID case the complexity was too big to, and in the IID case, essentially if you want your state to be like 1% close to a Bell state in trace distance, then you need on the order of 10 to the 13 measurements, I think.
not, let's thank Alex.